Hey there, and welcome back to a short little lecture about geometric attributes and some of their main applications. All right, so I'm going to start by talking about a little more than four, I got some bonus ones in there, a few different geometric attributes that are really common to use for seismic interpretation. We've got dip magnitude and azimuth, and then I'm going to talk about coherence and a couple of different ways we can calculate it. And then curvature, I threw in some shape index attributes and aberrancy. So we're going to start off simple and get a little bit more complicated. So we're going to start with dip magnitude and dip azimuth. And so dip magnitude and dip azimuth are kind of what you would expect them to be. So the dip magnitude calculates the magnitude of the dip in your seismic amplitude cube, and the dip azimuth tells you what direction relative to north it is dipping. And so one of the things you really want to keep in mind is that these aren't showing you true dip because we're working in velocity and not in depth. So just keep that in mind. And there's also a lot of different algorithms that you can use to calculate these. And so there are some other dip more instantaneous dip attributes that you can calculate too. I talked about some of the instantaneous ones in an earlier lecture. I didn't talk too much about instantaneous apparent dips, but they work well too if you have them available in your software. One of the ways that we can calculate dip that's a little bit more robust is by using the gradient structure tensor. And so this goes through the data and it allows you to calculate the maximum amplitude gradient. There's also the semblance search, which is one that I use fairly often. And so I've got a little kind of demonstration of how that works. So we've got our analysis point that I'm picking out with the orange arrow. We can go in, and in a lot of softwares, you can set those parameters. So in this case, the range of dips you want to test, and you want to kind of narrow that down if you know what's realistic, just for computation time. And so what happens is the algorithm goes through, and for that analysis point, it tries to understand what dip is giving it the maximum coherence. And so in this case, a dip of plus 5 degrees is the dip with the maximum coherence, so that's the one it'll register. And that's the kind of instantaneous dip at that point. And so if you do a comparison here, this is shown from one of Kurt Marford's figures, we could look at different comparisons of dip estimates on a time slice. So here we've got our simple instantaneous inline dip. We can look at our smoothed instantaneous inline dip, and then more of a multi-window scan of inline dip. So you can see the smoothed and the multi-window are fairly similar, but the simple instantaneous inline dip isn't great, and so that's why I don't tend to use it. Once you calculate and you go through your entire 3D volume, you can do some co-rendering of your dip azimuth and dip magnitude. And so that's what I'm showing here. So I talked about how you can take two different attributes. A lot of times we put one of them in a grayscale and then we make it transparent or slightly transparent. And so that's what I'm showing, where we've got the dip azimuth set in there as angles. So we can see it from plus 180 to negative 180, or kind of more the ordinal directions. And then dip magnitude is has zero opacity at plus 5 degrees, and then it increases up to 100% as the dip gets lower. So that really allows us to highlight where we have the more steeply dipping regions of this time slice. So just a couple of concepts to remember is that dip magnitude and azimuth are estimated in like a vertical window, and if we compare them to those around it, they can be a little bit more robust estimates. You can have distortions and errors with your dip and azimuth calculations. If you don't have really great seismic data, if you have noise in them, they can be kind of warped a little bit. And then also if you have things like velocity pull up or velocity push down, it will follow what it sees in the seismic data. Okay, coherence, my favorite attribute. And so as I've talked about a few times, coherence looks at how similar that one waveform is to its neighbors, or towards groups of its neighbors. And so there's a couple different ways to measure coherence and a couple different algorithms to do it. What I'm showing here is just one of the first applications of coherence back in 1995. And so this is the seismic amplitude. And as I pointed out when I showed this earlier in this lecture series, you know, there's some faults I could go in and pick out. I can see a salt dome, a salt feature over here because I know it's the Gulf of Mexico. So I'm using that kind of in-context interpretation. And I see a couple other few interesting features that I'd probably want to pay attention to. But if I ran coherence very quickly, I can suddenly have a lot more confidence in my interpretation. So suddenly I can see a lot of faults. I can see that salt dome. Here's that interesting feature I kind of pointed out that kind of caught my attention. And then we've got some channels, some very clear channels right here, but also kind of a shadowing of what looks like a bird's foot delta. So you can calculate coherence with a simple cross correlation, but there's other ways to do it. And two of the ways that we recommend doing it in my research group that, you know, where I do things, but is the semblance estimate of coherence. And so the way this works is the first thing you want to do is calculate the energy of your input traces. And then after that, you calculate the average wavelet within your analysis window. So this is our analysis window from the top to the bottom. And notice that we're doing it along dip. So this is really key. After that, you want to estimate your coherent traces by their average. Okay, so you're kind of like subbing it back in. And then you want to calculate the energy of the average traces. And so what you end up getting at each of these is a coherence, which is the energy of the average traces over the average energy of the input traces. And so if you have an identical waveform and they're very similar to each other, right next to each other, your coherence or your semblance is 1. And if it's not, then it's less than 1. And that means there's a little bit of a difference between them. Okay, another way we could calculate it is with the eigenstructure estimate of coherence. And so in this one, well, we start off with the traces, and then we calculate the seismic waveform that best fits the data within the analysis window. And I got those out of order. So sorry about that, but just like before, we calculate the energy of the input traces and then calculate the seismic waveform that best fits the data within the analysis window. And then from there, we estimate the coherent component of the traces. And so what we're doing is now this time we're replacing each trace with a scaled version of the waveform, which we didn't do in the semblance version. And then from there, we calculate the energy of the coherent component of the traces. And what we end up with is the energy of the coherent component over the energy of the input traces. And apologize for my little mess up in the animation there. So in any case, what the eigenstructure estimate of coherence gives us is it shows us, it focuses more on the exact same waveform, but it also takes into consideration if there's a difference in the amplitude. The amplitude. So when we look at what that actually looks like, here we've got our seismic cross correlation, the semblance, and then also our eigenstructure. And so a lot of times I've been finding the eigenstructure looks a little bit cleaner to me. But you'll want to, if you can, you may want to try them all out on your version and then kind of figure out which one works on your data and figure out which one works better for your data. And so coherence and the many different ways we can calculate coherence can be used to delineate channels like I showed you before. And so here we've got an example, a very classic example of the seismic amplitude, and then a giant kind of like bowl of spaghetti is what it looks like to me, of cross-cutting channels. It can also be really good for identifying faults and fractures. And so a lot of times when I show this in class, I'll just show the amplitude and I'll ask the students to pick out the faults. And they're really good at picking out the faults in the kind of horizontal direction here, but they miss all the faults that are kind of going vertically or kind of a long strike. And so like before, you can co-render the amplitude with the faults, and that can be really useful in kind of validating what you're seeing. All right, and so one of the last things I want to mention, because this is really key and it's, it's very important, let's just put it this way, is that it's really important to compute your coherence along structural dip. So typically the first thing you want to do in your software program is calculate the dip, and then when you calculate coherence, calculate it along dip, and that'll give you much better results. And so you can see if we're calculating, like all of us can pick out this bed by now, hopefully. Okay. But if we calculate coherence just along time slices, it's going to look like a very low coherence. Whereas if we calculate dip first, we'll notice that we get a much higher coherence, and that's more geologically accurate. Like, we should be doing these attribute measurements along dip. And so this is an example of what can happen on the left-hand side if you calculate the coherence along a time slice. Instead of seeing the faults, you actually get this kind of like structural leakage, and almost looks like contours, because you're sampling above and below the horizon that you're actually interested in. But if you calculate the coherence along structure, it's nice and clear and clean cut, and you would have much more confidence picking faults when you calculate it along structure than along structure and along dip than you would without it. And so just a couple of key concepts with coherence. So it is, as I've mentioned, a great tool for delineating geologic boundaries, whether they're stratigraphic, channel-related faults. I'd mentioned that I use it for QCing, so it's really great at quickly evaluating a larger data set. It can give you information about faults and fractures, stratigraphic information, and I put this in red, but you should always calculate it along dip. All right, and of course, if you have any imaging problems from acquisition or processing, those are going to appear, like there's still going to be problems in your coherence in terms of interpretation. So moving on to the last group, we've got curvature, shape index, and aberrancy. All right, curvature is actually the derivative of coherence, and sometimes it's called roughness, and so coherence is a derivative of dip, curvature is a derivative of coherence. And I always like to refer back to this image right here, because curvature tells you how curved a surface is. And so if you have an anticline, you'll have a positive curvature. If you have a flat dipping plane or just a flat surface, you'll have zero curvature, because something that is flat is not curving. And then a syncline is negative curvature. And so, a lot of times when I'm doing slides or presentations, I always put this little schematic on there because it's really helpful. And then the higher K, which is the curvature, that's the more curved the surface is. So you can imagine if you have a large scale dome as compared to a small, maybe like levee or axis of the channel, those will have different strengths of curvature. And so this is kind of another example from Kurt Murfert, just kind of showing what it looks like in terms of a nice outcrop image with a curvature of 0 wherever you have flat dipping planes or flat planes, the negative curvature with synclines, and the positive curvature with anticlines. So here's an example of most positive principal curvature. This is working in the Great South Basin of New Zealand, so one of our example data sets that we use all the time. And so we can see here quite a few interesting lineations. We see some structures. We can also look at the most negative principal curvature, and it really highlights a lot of faults, and it looks like some smaller scale, maybe we would call them fractures. We'd have to understand the geologic setting more before doing that. And so what's really common is to co-render both of these at the same time so that you get the positive and the negative. And what's interesting is that a lot of times in channel systems is you can see the axis of the channels and then the levees on either side of it when you do the co-rendering. Another way we can use curvature, K1 and K2, is to calculate the shape index. And so this is doing just a quick mathematical computation using those two variables that we calculated. And if you have a shape index that's kind of between -1 and -0.5, those correspond to a bowl shape. You can also calculate valley shapes, saddles, so kind of like a saddle, like I'm showing here in green, ridges, and then also domes. And so these can be really useful, particularly if you tie them to a good color bar, as ways to show smaller scale features in your seismic data. And so in this Great South Basin data set, we have a lot of pock marks from synuresis. And so those are really interesting to see, and I'm trying to show them here, where the red colors are those dome shapes, and then the bluer colors are more of the bowl shapes. So we're getting a really good idea using this shape index and these colors of what exactly is going on down there. So here's an example just showing now the geobodies calculated from grabbing all of the bowl-shaped ones, so the blue ones in the last example. We've turned them into geobodies, and then we're displaying them on a coherence time slice, and you can see we've got our seismic amplitude shown in the vertical section. So a really good visualization, combining the seismic amplitude, coherence, and then also geobodies extracted from the shape index of a bowl. And then finally, I'm going to wrap up with aberrancy, which is it's a newer-ish attribute. It's probably only been around for 5-6 years now. And what aberrancy is it tries to look at areas or tries to let you see areas where you don't have that full offset that you would have in a fault. So I'm going to walk through these one by one. So if we have clear offset, it's well imaged, we can image that with coherence. In some cases, our imaging isn't quite as well, but we have that fault offset, maybe with some conjugate faulting, maybe the imaging isn't so good, so you kind of get that dragging shape. You'll actually pick up here the edges of the fault because of that drag and that curve with your K1 and K2 curvature. If you're below resolution, you may not actually pick up the fault offset like I'm showing in the lower left with coherence, but you could pick it up still with curvature. And then in some cases, what's really nice is that you can use aberrancy to actually look at it's the derivative of curvature, and so it'll actually see what's between your K1 and K2. So let me show you an example of what that looks like in seismic data. So we're going back to the Great South Basin. Here we've got our aberrancy. We've got the total aberrancy azimuth shown with colors, so the direction that we're seeing kind of that dipping feature. And then we've got the magnitude of it. And again, we're using a opacity tool so that we're just seeing the higher aberrancy areas. So where it's grayer, that's much lower aberrancy. And so we're not really paying too much attention to it. And so what it's showing is a really nice image of areas where we have a lot of smaller scale faults. And so when we compare that, so I want you to look at these white arrows here and then this yellow arrow over here and the features that they're pointing out, because what I'm going to do is I'm going to flip to energy ratio similarity next. And so that one fault over here marked by the yellow arrow, we can pick up pretty well on energy ratio because we're getting a better separation if we were to look at the vertical slice. But this area that is heavily faulted and fractured, it isn't being picked up very well on the similarity. And so this is one of the reasons it's really good to run aberrancy, is because it's much more sensitive to smaller scale faults that may be below resolution. We've actually done a lot of studies with this lately in the basement to look for basement faulting, where the noise, there's, like you just don't have the resolution, it may be noisier. And aberrancy has been a really good tool for us in the basement. We've tested it out in a couple of different areas, parts of the world. All right, so to wrap up with this lecture, I talked about a couple of different geometric attributes from dip, azimuth, dip magnitude, coherence, and now curvature, the shape index, and aberrancy. And so we want to keep in mind that all of them can show us something very different. I'll show some examples in later cases when we go into certain depositional studies about how channels really show appear well in curvature, particularly if you have that differential compaction or you have those levees on the sides. But curvature is also really good for faults, as is aberrancy. And so thank you very much for listening.